quasi-2D waves more isotropic. Could be this the reason?
Yeah, but like I have very good like story about that. I mean, say so because we have mathematical conference. So this your very simple question is basically related to very important area of mathematics, which is called Riemannian geometry. It looks that it's completely two different worlds, but it's indeed related to it. And then, because basically what you do, you can say like in some naive way, how like Einstein used in special theory of relativity, what he measured distance by arrival time of light to different points. And this was all there. Here you can say the same. Let us measure distance in the heart by time when electrical wave arrives from one point to another point. And then this arrival time will allow you to introduce metric in this space. As you know, like in relativity, they have like Minkowski space and like some other space and so on. But here, because we have just two orthogonal directions, where, for example, in this direction different than in other direction, then we got a classical Riemannian metric in this space, and so on and so on. And then when you look to this Riemannian metric, then as you know, like as in general relativity, etc., the shortest path of wave go from point A to B is not a straight line, but it is so-called geodesic, when you follow like some specific direction, which is solutions and so on and so on. Now, assume the following. We have, like how you exactly told, you have a slab of cardiac tissue, and we have rotation of fibers, assume simplicity 180 degrees, that all angles are present. And I ask you, I take point A and point B, which is very far from point A, and what will be geodesic in that case? For that, you do not need to solve these complex equations, etc., but you can just assume the following experiment. You have point A, point B. You just project them to a plane, and then you will get a direction from point A to point B. Then what I tell you, because you have all possible fiber orientation, then geodesic in that case will be, you go from your electrode to some thickness when you have fiber which exactly goes direction, then go along this fiber and then go back to it. And if distance is very far, it will be exactly. Therefore, you get from this simple explanation very interesting result. Like it was also very interesting for me that basically when you have rotational anisotropy, then velocity of wave propagation, for example, in one direction, you have velocity 1, in other 0.5. But if you have fiber rotation, then velocity will approach not average, not 1 plus 0.5 divided by 2,
but the fastest
will approach 1. And therefore, this is approximately what we see in Darius case, because when you have rotational anisotropy in the heart, wave rotates fast as if it is isotropic, but isotropic with highest velocity. And therefore, this is approximately like how it works. Okay.
Thank you. So I wasn't too far from the right answer. Any other question, colleagues? We have 5 minutes left for the next talk.
Well, if you have several minutes and no other questions, I would suggest that Andres, it's our next speaker, tries to share a screen to make sure that it works, because we have not verified it before. So Andres, please, if you hear us, you can check your screen. Well, no answer. Andres, do you hear me, Andres? It looks like he is present, but no answer. Ah, yeah, okay. Andres.
I am here. I am trying to show the slides.
Yes, please show your screen.
Let me 1 minute, please. Okay, please. This is my presentation. You tell me when I can to start.
Yeah, so Andrei Saturian
Yep.
chairing this session, so he will.
I think we could wait for 5 minutes in case somebody is going to listen to your particular talk. Couple of minutes. Your talk is scheduled for 17:05, so 2 more minutes. We can wait. A very rare case, so disciplined speakers. Everyone was in time. Even faster. Very unusual.
Yeah. We ask speakers and chairman to respect time schedule, because people sometimes just go come from other places from all around the world, and they can, with all the time differences, so they can come to listen to some particular talks. So this is why better to respect our time schedule.
Vitaly, I see that all the people are from Russia.
No. We have now about 20 participants, listeners, and some of them are not Russian speaking. So
Okay.
I know that you like speak Russian, but we will invite you for the seminar in Moscow, so you will speak Russian. But now it's better to speak English.
Okay. I try to speak in English. The English for me is very difficult language.
Oh, really? But we have here Christina Leon, who is my graduate student, and she speaks Spanish. Well, I'm not sure that she can do simultaneous translation, but maybe she can help us.
No. It is not necessary simultaneous translation. For some explanations, maybe will be necessary.
Okay. Andres, yeah, so it's time. Please press the button to show this full screen where you're.
Okay.
Great. Thank you. Go ahead.
Yes. Okay. My talk is about theoretical results in some mathematical models. There is not an investigation that this have some practical basis, experimental basis. Only I try to show some theoretical evidence of transition to arrhythmias in some cases, in some particular cases, cases that when the arrhythmias are produced by disruption of the cardiac cycle, or by some genetic illness, channelopathies, like in the case of Brugada syndrome. This is the type of arrhythmias that can be produced, and I start from these commentaries. I studied two fundamental problems, theoretical problems, in the study of the cardiovascular systems, mathematical and numerical analysis of lumped parameters model for the cardiovascular systems, and mathematical modeling of the electrical activity of the heart using the monodomain and bidomain models. In the first part of my talk, I will talk about mathematical and numerical modeling of the cardiovascular systems using special lumped parameter model. I am not working in distributed parameter models of the flow of the blood in the cardiovascular systems, and only these models with use ordinary differential equations and allows less detailed descriptions of the system, but these are models that are capable of providing useful information on cardiovascular hemodynamics in the setting of diagnosis in the intensive care units. These models are very known, are models segmented by compartments. I use a very simple model that contain three compartments. Here I explain why these models are useful. And the work is related to the first part of this work is related to the study of the cardiac cycle for the left part of the heart, the cardiac cycle that involve the subvolumetric contraction and ventricular ejection in the systoles and the subvolumetric relaxation and ventricular filling in the diastole. The purpose of this study is to find conditions that ensure the periodicity of the cardiac cycle in an appropriate lumped parameter model of human blood circulation when the heart beats occurs with a constant frequency, omega. The question is not only the demonstration of the existence of periodic solutions of this model, but rather that these solutions reflect the existence and periodicity of the four phases of the cardiac cycle. This is the more important. Here there are some images about the cardiac cycle and the relation with the electrocardiogram, the phonocardiogram, and the ventricular volume, the pressure volume loop that explain how these phases appear. The model that I consider is this model for with three compartments, very simplified model of three elastic chambers, two vascular segments for describing the properties of the aorta and the vena cava, another compartment for modeling the left ventricle. This model only considers the opening and closing of the mitral and aortic valves and a representation of the capillary resistance. This is the model for the three variables, the volumes of stressed blood volume of the left ventricle, of the arterial section, and the venous section. Here is the model. This is a variant of a very known model, more complicated. These are the definitions of all the variables that include the model. Here we have a very important term in the model is the elastance of the left ventricle. This is a very high nonlinear model. Okay. This is a description of the variables and parameters included in the model. The three stressed blood volume, the three pressures, and the blood flow through the mitral valve, the aortic valve, and the flow in systemic capillaries. The importance of this work is the formalization of the concepts that are related to the cardiac cycle. The formalization of the concept of elastance function for the left ventricle. For us, the elastance function is any real function that satisfies these properties. A particular case of this kind of elastance is this function that is used for numerical computations. The electric analog of this model is shown in this figure. Here we have the compliance, that this is the reciprocal of the capacitance of this in these circuits. Here the resistor RS denotes the resistance to flow in the systemic capillaries, and the aortic and mitral valves are represented by a resistor-diode combination. The model can be simplified to a system of two ordinary differential equations because of these properties. The sum of the derivatives of these volumes is zero, and because of that it is sufficient give the model for two of these variables. This is the model that we obtain for two stressed volumes. Here H is the Heaviside function. Q represent QAO, QME represent the flows. And now this is very important for this work, is the formal definition of the hair mechanical cycle in terms of the variables of the model, of this model. In terms of the variables of these models, we give 5 definitions. The first is the concept of, that means an initial condition of the beginning of systole. An initial condition of the beginning of systole is an initial condition that satisfies these properties. These properties are given not for free and are given as are related to the definition of the beginning of this period of the cardiac cycle. After we give, these are some variables that are included here in this definition. And after we have the definition of the isovolumetric, what's mean that in some interval, the solution corresponds to the isovolumetric contraction, to the ejection, to the isovolumetric relaxation, and to ventricular filling. These are these four definitions, and the main results of this work is that if T is the period of the ventricular elastance function, and we suppose that the initial condition satisfies the condition of the beginning of systole given in the definition 2, that involves the corresponding ventricular elastance function. Then, if, in this case, there are constants T1, T2, T3, and T4, such that the corresponding solution of the three chambers model reproduce the four phases of the cardiac cycle in the sense of the definitions. And this solution is periodic with period T. For the demonstration of this result, we use the Brouwer theorem about fixed point applied to the point current mapping associated to the model. Furthermore, the definition 2 that describe the conditions for the beginning of systole characterize the set of initial conditions that correspond to periodic solution of this model. That correspond the periodic solution of this model that reproduce the four phases of the cardiac cycle. This is the important thing. Okay. Here we have some numerical results where we use the values, the corresponding values of the parameters for normal heart. Here we use these parameters. We use this expression for the elastance function of the left ventricle, and we obtain the periodicity for the volumens, for the pressures, and for the blood flow. In the when we use this initial condition for the beginning of the systole, that satisfy the conditions of the definition 2. Okay. Then I introduce the second part of my talk about the mathematical models of generation and spreading of electrical activity in the heart. I explain here, but maybe this is not necessary. What is the B-domain model and the monodomain model as a simplification of the domain, assuming that the intracellular and extracellular currents conductivities are proportional. I said that it is shown that the difference between the two mentioned models are small, even if extracellular potential are influenced by fluid-filled cavities. Because of that, in some part of our investigation, we use the monodomain model for the mathematical formulation of the reaction diffusion model that describe the start and spreading of electric currents in the heart. This is the very known monodomain model. For the theoretical results, in some cases we use the Royer-McCulloch model for the ionic currents, and in other case we use a theoretical expression for the F ion, for the ionic currents, and these are the explanation of the terms of this model, and that what describes each of this equation. The second equation is the equation that describes the activation and inhibition variables for the ionic channels. The anisotropic characteristic of the conductivities are given by the tensor sigma here, and Cm is the cellular membrane capacitance, and here the most important is the activation of the endocard. The activation of the endocard is given here in this second boundary condition in gamma 1. Gamma 1 represents the endocard, gamma 0 represents the epicard. This is the model for an isolated ventricle. And we here include the source not as a term of the monodomain model and as a term of the boundary conditions. This represents the activation of endocard through Purkinje fibers, and ST we assume that is a periodic function that represents the sinus rhythm and correspond to the periodic activation of endocardium, which is given through the Purkinje fibers, and function phi represent the spatial density of activation, and thus the product of ST and phi x represent the external current source in the model. We do some necessary change of variables and time reparametrization. This is important for obtaining the result, the main result. We introduce new variables, omega without this chapeau, and a new time tau. We introduce this parameter phi and epsilon that play an important role for the demonstration of the main result and not alter the result. The result that we will obtain is related to the when this model has periodic solutions. In what sense have periodic solutions? Okay, when we do the necessary change of variables, we obtain a new model very near of the monodomain, the first monodomain model. Here the function f acquire this form. These are here are the description of all the parameters. After, if you are interested, you can see the details. We introduce some auxiliary functional spaces and linear and bilinear form defined on them. The principal spaces are the space of L2 on the region that is occupied by the ventricle omega, and the subtle space H1. I represent L2 through H and H1 through V. And we construct the Gelfand triplet associated with V and H. And for this Gelfand triplet is associated duality product that satisfies this property. And we define the functional phase star given by this functional, and also the bilinear form defined in V through this expression. Why we introduce the change, the reparametrization of time? Because here appear the parameter epsilon, and then we have this is important for the technical apparatus that we use for the demonstration. The operator A that represent this bilinear form is a bounded sectorial close densely defined operator that did describe this is a cell of joint operator in H, in L2, that has this domain and act with this expression here. And this is a cell-adjoint positive, strictly positive operator with eigenvalues that have tends converge to infinite, and has an associated sequence of eigenvectors that is an orthogonal basis in H. The definition of weak solution, we give then the definition of weak solution of the modified monodomain model. This is the definition of weak solution. It's very natural. Here the only thing is that the properties of this weak formulation are given in terms of the derivative is defined in terms of generalized functions, is distributions, and we define when the weak solution is a local weak solution in the interval E. I. If the pair U omega, that is the solution of the monodomain reaction diffusion model, satisfy these conditions in sense of distributions. Then we sketch the proof of the fundamental result of the system of a global weak periodic solution of the modified monodomain model. We use we construct for each integer the Faedo-Gallorkin system associated with the weak approach to the modified monodomain model, and obtain this system of 2n+1 ordinary differential equations for the coefficients of the approximation of the solution of the monodomain model, and use the idea of Farkas developed in his book Periodic Motion, combined with the Schauder fixed point theorem, to show that each Faedo-Gallorkin system has a periodic solution under certain conditions on the ionic diffusive parameters of the monodomain model. This is the important thing, how is related the systems of periodic solution with the ionic diffusive parameters of the model. That this result permits the interpretation of the effect of some anomalies in the transition to the algorithms, as I will set in the next minutes. It is necessary to select conveniently the values of the parameters that appear in the change of variables and time reparametrization, but time reparametrization not change the periodicity of the function of the solution. Furthermore, it is shown that the corresponding sequence of periodic solution is uniformly bounded in age. This is our result. And then, using an auxiliary theorem also from another result, our result, it is shown that the Faedo-Gallorkin approximation sequence has a weakly converging subsequence to a global weak periodic solution of the monodomain model. Here there are some necessary notations that involve all the parameters that are included in the model, all the parameters, and not only directly the parameters, and parameters as the norm of the trace operator of B in L2 of gamma 1, where gamma 1, I remember, is the endocard. Taking this is a very, I consider this is very very well resolved, but because involves all the geometric characteristic, not only electrical characteristic and characteristic of the ion channels, and characteristic of the geometry of the ventricles. And if we introduce these functions ht and pr, when t is related to the period of the periodic of the activation of the endocard, and r is related to the height of the solution in that sense that I said immediately. This is the main theorem on the existence of periodic solution for the main model. If we assume that the ionic diffusive parameters satisfy the relations, this relation is always maybe C3, that is parameters that appear in the in the model for the ionic currents and not satisfy this condition, but the product by C satisfies because we select the parameter G that satisfies this first relation. And the other relation is this one with air. I now said the means of air in this theorem. Air with a star is represented by this quality. Then the result is that we obtain two intervals, Rmin, Rmax, and Tmin, Tmax, such that for all air in the first interval, there is a T-periodic global weak solution of the monodomain model, for each T in the interval Tmin, Tmax, such that HT is less or equal to PR. This periodic solution satisfies this estimate. This is here is appear error in the estimate for the solution. That is, the periodic solution belongs to the ball with center at 0, 0 and radius r in the Banach space of the continuous and periodic functions of period t with values in V cross H. An observation here in our work.
I'm sorry. Can you please speed up? We are running out of time. So could you please more or less summarize your talk, please?
Excuse me, you can repeat?
Of time, so please summarize your talk. Otherwise, yeah.
I need only 3 minutes to finish.
No, you have only 2.
Okay. The observation, this is a very important observations. The interval, this interval, everything seems to indicate, although we have not yet proved it theoretically, only numerically, is the interval of the admissible frequencies of the cardiac rhythm out, that is, out of this interval, the hair eventually loses its periodic rhythm. And this is important because this explains why a person with Brugada syndrome can have ventricular fibrillation when their sinus rhythm is at low levels corresponding to the state of rest. Indeed, we have verified that when the parameters of the ionic current correspond to those of a person with Brugada syndrome, then Tmax is sufficiently small such that the lower limit, this one, of the activation frequency required for the existence of rhythmic activity in the hair exceeds the values of the resting sinus rate. In this case, the activation frequency at rest would be outside of the admissible range of hair rhythm frequencies, producing ventricular fibrillation. I finish with this. This is we study also the Cauchy problem associated with the torso-bidomain couplet model. We are interested in this problem for the solution of the inverse electrocardiographic problem and the determination, not only the obtaining of the potential on the epicard, that is the classical inverse problem, and also obtain some properties of the hair that are related with abnormal electrocardiographic signals. We start by defining the torso-bidomain couplet operator and study its properties. From this operator, the Cauchy problem is reduced to a problem with initial conditions for a system of abstract evolution equations for which the concept of global strong solution is strong, not weak. Strong solution is defined. We conveniently construct a Faedo-Galiorkin scheme associated with the variational formulation of the abstract Cauchy problem, and under certain conditions, on the term that describes the ionic currents in the B-domain model, it is shown that the Faedo-Galiorkin approximation converges in a strong sense to a global strong solution of that problem. This is this work, and using this result, the system of periodic solution in the strong sense is demonstrated under conditions similar to those obtained for the monodomain model. Now, the most important is that these approximations are also very useful to simplify the numerical solution of the inverse electrocardiographic problem and allow obtaining the values of the ionic diffusive parameters from electrocardiographic measurements of abnormal activity. This is a work in progress. I finish with this. Thank you very much for your attention.
Thank you very much for your interesting talk. We are running out of time, so maybe one fast question is the most we can afford. Please, if anybody has a fast question, please. Vitaly?
Yes, thank you, Andres, for this really very interesting presentation where you bring together this mathematical study with these very important applications. Unfortunately, indeed, we don't have too much time, so I will ask a short question. But if it takes much time, then we can discuss later. But you mentioned some conditions on ionic currents.
So not only ionic diffusive.
Diffusive. So could you explain very shortly, but not with mathematical formulas, but just biological meaning of these conditions?
It is difficult. It's difficult to mention this because you see the definition of the parameters that are included in the conditions. They are not directly the definition of the parameters that appear in the model. But I give an example. If I present, a ver, Stephanie, ¿cómo se puede compartir? Ajá. Aquí, ¿le doy? Ajá. 1 minute. Ajá. Because of that, I put this slide. This slide, this observation. This is the kind of thing that can give the practical meaning of these conditions. You obtain that this interval is the interval of the admissible frequencies of the cardiac rhythm. The definition of Tmax and Tmin depends of this of the ionic diffusive parameters, and then if this is very important, the value of Tmax, because this value define the inferior limit of the admissible frequencies that are admissible for the cardiac rhythm. This is the frequency of activation of the endocard, and not always the frequency of activation of the endocards produce a cardiac a periodic solution, a cardiac rhythm.
Yes, thank you. I understand. Yes, that well, in fact, this biological meaning is inside this T-min and T-max. So yes, thank you very much. It's really
Thank
very
you very
interesting.
much.
We do in our work, we do some numerical experiments that explain your question, but for me it's difficult to explain this in 1 minute.
Thank you again.
Thank you very much. Thank
Thanks.
you. Yeah, just remove your presentation, your screen. Remove your screen. Great, thank you very much. And
Thank
we
you.
have to move to our last talk, please.
Salir aquí.
Can you show your screen?
Okay, so let me check. Let's stop. Okay, so please let me know if you can see my screen.
Yeah, great. Yeah, we can see
Great.
your presentation.
Okay, so
thank you very much. Carry on.
okay, no problem. So I assume you also can hear me correctly. So yeah, hopefully it's going to be a brief talk, much less theoretical than the one previously. So yeah, so thank you all for coming to this last presentation. My name is Arostica, and today I'm going to talk about on Chorin-Temam schemes in moving domains and its application to left ventricle FSI. Importantly enough, this is a joint work with Cristóbal Bertoglio, who is currently the leader of our group at the University of Groningen in the Netherlands. So briefly, this talk is divided in 5 main sections. First of all, I'm going to give you a brief motivation of this talk, essentially. I'm going to provide then the moietic schemes that we studied. We'll move then towards Chorin-Temam schemes and their results. That will allow me to introduce the cardiac mechanics, the benchmark, and of course the FSI simulation. And finally, a brief summary. So first, the motivation. So the incompressible Navier Stokes in moving domains allow us to model several relevant problems, primarily in the context of fluid-solid interaction. Things such as aerodynamics or physiological problems are one of the main cores and targets of it. In this context, cardiovascular contraction, and in this case, left ventricle contraction is very important. And in such a direction, one question that we want to address is the one of efficiency. And in such case, Chorin-Temam schemes are kind of useful. And so I'm going to provide you in this talk a result we obtained with Cristóbal Bertoglio regarding a Chorin-Temam scheme that's unconditionally stable, or say correctly, unconditionally energy stable. So to go towards that direction, we first studied moietic schemes. And we found out that there are many authors and, of course, many different ideas. But nevertheless, we were able to kind of obtain a general formulation for the first order in time derivative. So given B and Q finite element spaces for the velocity and pressure, the problem that I'm interested in is defined by the calligraphic operators A and B that describe the incompressible Navier-Stokes equation in this arbitrary Lagrangian Eulerian formalism that is suitable for moving domains. Here you see the J, H, W. What they represent is, in this case, J, the determinant of the deformation gradient, H, the inverse of the deformation gradient, and W, the velocity of the domain where the flow is currently in. Also highlighted in blue is the so-called discrete residual of the GCO. What it stands for is the geometric conservation law that arises naturally from our formulation in this arbitrary Lagrangian Eulerian formulation. Here, I added into the formulation with a parameter alpha that can be 0 or 1, and I also include beta multiplied by the Temam stabilization term. And so the main question now is how general this formulation is. The answer is that we found that it's quite general. In the case that we do not take stabilization terms, meaning we take alpha equal beta equals 0, we have at least 4 different articles. We have the work done by Basting, by Miria, by Langer, and Alajuela. You see this star, 2 stars, asterisks, 2 asterisks. They represent different approaches to define the scheme, as it could be in fully implicit schemes done by Langer, or some sort of combination, as can be done by Landajuela or Miria. In a similar fashion, there are also works done where they include the stabilization terms, meaning the Temam stabilization term that I showed before, and also this GCL term. And we can see, for example, the work done of Losovsky, of Maldon, Letalec, Wang. I have to highlight the work done by Losovsky, who also provide first the GCL stabilization term. He provides also the Temam stabilization term, as well as stabilization and energy analysis of the scheme. And so there are quite a few persons working on it. So having defined this moietic scheme that I previously showed, what are the main results? First of all, something very important and classic. So if you assume well-posed orientation preserving deformation mappings, meaning Jacobians and bounded positive, then moietic formulation has a unique solution for stable finite element spaces if a specific condition on the Jacobians and if we include the stabilization terms, meaning alpha equal beta equal 1. Then what does it mean, this J, this condition of the J? It means just a condition on how rapidly the deformation of the domain can be. Next, what's the main result in this small section? The main result that we found out is that if we include stabilization terms and moreover this 2 star equals n, which means that we take an explicit approach for the domain, at least in the term of that includes the time derivative, then the moietic scheme is unconditionally energy stable and with estimate given as in the screen. And importantly enough, there are no restrictions on the other possible choices that we can take for the pressure term, for the convection term, as is described here by no restrictions in star, asterisk to asterisk. So having said that, we have already that this DCL thing is very important. And so what can we say about Chorin-Temam schemes? Can we obtain something similar, which is the main goal? The answer is yes. So to get into that answer, let us define in a similar fashion as before, tilde B and tilde Q conforming finite element spaces of the velocity and pressure. And then we define in a very standard fashion the Chorin-Temam scheme through a 2 steps approach. First, through a pressure projection step, and then through a viscous step. Here, you have to notice that I have given this circle that can be a different choice of the scheme. It could be n and minus 1. And similarly, for the fluid viscous step, I have 2 asterisks, 2 circles, 2 stars that also are possible choices that I can take for the scheme. Also highlighted in blue is the GCL stabilization term, as well as the Temam term, not highlighted, of course. So under such a scheme, we again studied stabilization, and we found out the following. If we first consider circle equals n, meaning that the pressure projection step is implicit, and then 2 circles equals 2 stars equals n, meaning that the fluid viscous step is explicit, and the solution of the CT formulation is unconditionally energy stable, given by the estimate in the box, where no restrictions apply on star, meaning on the diffusion term. So this is a very important result, we think, because it provides us a very useful approach to work in FSI. And so what's the next step? We found theoretical bounds. Let's see if numerically we can achieve those. So here I'm going to show you a test case in 2D, and then I'm going to make a connection towards 3D. So in the 2D case, I propose a rectangle where I'm going to simulate the Navier Stokes equation, where I impose three homogeneous boundary conditions. I assume a deformation mapping described by this calligraphic X, which is essentially just an oscillation in one coordinate. And I also assume, for this toy example, that the velocity is not, the initial velocity is not zero, and it's given by a parabolic formula. So the next question is, what should we measure? As you see by the propositions I have shown quite rapidly, I have to say, the terms have a specific condition. So what happens, and the natural thing we should do is just put every single term from the energy propositions to one side and just check what we get as residual. And this is what we did. So the results are assessed using time-varying normalized parameters, this delta M and delta CT, associated to the monolithic and Chorin-Temam schemes. And then we test for two different monolithic approaches and for two different Chorin-Temam schemes, where here is highlighted in blue and in red the good case and the bad case, where the bad case in this case, where the bad case here means that I'm not satisfying the conditions I have obtained. And so from the previous propositions, as I have told you, we should have that this delta M is 0 for every time M, and delta CT is less than or equal to 0 if we take 2 stars equals N, meaning we're in the right choice of schemes. And so, what are the results? Using the simple simulation, we found that we're able to satisfy up to margin error the bounds that we have obtained theoretically. You see on the left side in a dashed line that in a good case, meaning 2 stars equals N, this parameter delta is 0. And on the right side, for the Chorin-Temam approaches, we see that the scheme where 2 stars equals N is much more diffusive. So now towards the case of 3D. So here the question is, which example should we take? Which example is useful? And of course, can be extended towards useful scenarios. And so this is the reason why we came up with the idea of trying to create a new benchmark. And of course, in our field of expertise, which is cardiovascular mechanics. So towards cardiovascular mechanics and FSI. So why a benchmark? Or maybe rephrase the question, why a new benchmark? Because this is not a new idea. First of all, we want to address the reproducibility of others' results and also support collaboration with clinicians. A common question that arises when you try to work with them is the following. Have you validated your data? Is there some example or some test case that is realistic enough and also provides good results? Good results meaning physiological results. This is not new. For example, the work done by Lan in 2015, in which he proposed a first benchmark for cardiac mechanics, we notice that it lacks several relevant characteristics and features. Things such as appropriate geometric dimensions, for boundary conditions, and of course, a dynamic formulation is required in our perspective. Thus, we aim to propose a new set of cardiac benchmark problems and solutions for assessing the passive and active material behavior. So what's the formulation we are proposing? So we take a, what's the name of this? Elastodynamic, or better name, viscoelastodynamic formulation of the problem, meaning of the solid, where here you need to imagine this domain omega characterized as the boundary or the solid in which the heart contracts or the left ventricle contracts. We impose Neumann boundary conditions as well as Robin type boundary conditions. Highlighted in red is components that are not present in the current existing Lan's benchmark. And also, the Robin boundary conditions define, from a physiological perspective, the effects of the pericardium within the whole cardiac contraction, as it was studied by Martin Fowler. So, what about the constitutive model? Here we take the second pillar Kirchhoff stress tensor that define our solid by three main components. We assume first a Hobsbawm-Ogden formulation for the anisotropic term of the energy with a Simo-Miehe incompressible penalty described by the last term. We include also a viscoelastic parameter, a viscoelastic energy term with a parameter eta, and we also include a time-dependent stress tau of t multiplied F cross F for F, the fiber direction, where this tau t is a stress function described by Bessel, which is a solution of a specific ODE that arises from biochemical assumptions. So what about the test case? In the simulation you see here in the video is simulation for P2 elements where we include a pressure equals 0 on the endocardium, the interior, with a numeric beta time synchronization scheme and Martin Fowler material parameters. Importantly enough, and it's not mentioned here, is the fact that this simulation for P2 elements takes around 100,000 degrees of freedom. Now, about the FSI. We have already defined the solid, which roughly makes sense and roughly obtains what physiologically it is in, of course, our restricted domain. So what if we put a volume inside and we simulate Navier Stokes equations? And in particular, given the fact that we have this CT scheme that we know the sound condition is stable, let's put one specific scheme of those inside. So in that direction, we implement such a FSI algorithm that is described in this scenario as a semi-implicit FSI implementation. It's defined through three main steps. First, a lifting step where, given the displacements obtained on the solid, we extend those to the fluid. Specifically in the simulations we are going to see through an harmonic lifting. On the fluid, then, we solve for the tentative velocity denoted by U tilde. Such tentative velocity, then, allow us to compute this residual, what I'm going to explain in just a moment. So the whole point is just iterate over the residual until it reaches some tolerance. So how do you compute this residual? Having defined the tentative velocity, then we solve for the pressure, of course, in the fluid. Having computed the pressure, it allow us to compute the force that the fluid acts on the solid. Having defined such force, we compute for this displacement of the solid, and we retrieve this S prime, which denotes the derivative of the solid problem. Why we retrieve that thing and we keep it safe? Because we're able to obtain and we're able to use it for the tangent step, which is essentially a way to update the displacement through a fixed point problem. Finally, if we having computed this tangent step where we use GMRS and it's quite cheap, we update displacements defined by this expression, and then we compute the residual, which is a difference between a tentative displacement on the solid given at the interface minus the one we already know. This algorithm is not new at all. It was first defined for a monolithic case by Gerbo and Vidrascu in 2003, and then extended for a Chorin-Temam case by Bertoglio, Cayasso, and Fernandez. So what the simulation now looks like and how this simulation compares to a simulation where there's no interaction. So as you see here in blue, on the left side, the simulation with FSI, and on the right side, a so-called one-way approach. What it means one way is that we contract the solid, and then we extend the displacements on the solid to the fluid. Nevertheless, the fluid never affects the solid in any sort of fashion. So what you see here, let me repeat the simulation, is the fact that the solid contracts much more naturally. And of course, it's not given in this presentation. We are able to obtain much nicer ejection volumes. Then, what's the summary of this? So I've been quite quickly, I think I'm just in the right time. So to the best of the author's knowledge, the unconditionally stable Chorin-Temam scheme derived here has not been reported yet. Something very important is that the literature lacks a physiological cardiac mechanics benchmark. And I think personally, there is a big gap that needs to be filled in, and a lot of interesting ideas can be used in that situation. Finally, this semi-implicit FSI algorithm that couples this CT scheme with a solid provides a very efficient approach. Nevertheless, I must say I haven't presented enough pictures to discuss this efficiency. So hopefully this presentation, which is the last one, is nice to you. Hopefully you got a good time. If you're interested in our work, please contact Cristobal Bertoglio or myself. Thank you. So finally, on the left side, if you want to just take a quick look with your phone, you have the website of our group. And on the right side, the current benchmark we're working on. And of course, you are more, if you want to join us, please be free. And thank you.
Thank you very much for your interesting talk. Any questions? Could you specify these last pictures where you've shown this fluid structure interaction? Is it 2D axisymmetrical or 3D model?
Yeah, this is a 3D model. Yeah, so probably it's not the best. Yeah, it's not the best view, but yeah, this is a 3D model. So of course, here you see a 2D because it's just a picture. I just want to emphasize what it means, each part, but the simulation is 3D. So you have here fibers that are trying to imitate the configuration of the heart, of the left ventricle.
Well, the reason I'm asking is that some people see some rotating flow in the left ventricle during both filling and injection. So in principle, you can set your boundary conditions to have some rotational moment and see how it evolves in time during the cycle. So is it possible?
Yeah. Now that you're asking me that, I think that might come from choosing a different domain. So this domain is very idealized, but if we look for a more realistic domain or mesh of the heart, I think we're going to be able to see such type of artifacts.
So it looks like it's not an artifact. It's just because from the atria, blood going from atria to left ventricle, it has some asymmetry. So there is some momentum which remains because of high Reynolds.
Okay, I got it.
Yeah, it's more or less systematic observation.
Okay, great.
Right, thank you. Thank you for very questions, colleagues.
No one.
Yeah. Probably audience is a bit tired.
Yeah, I think so.
Thank you very much for your talk. Thank all the speakers and all the listeners for this session.
Yes, and on my side, I would like also to thank all speakers and our respectful chairman. And I would like to recall everybody that tomorrow we'll have another very interesting day of our workshop. So you are very welcome to participate. So bye for now, and we'll meet tomorrow morning.
Thank you,
Thanks.
Vitaly.
Thanks.
Bye-bye.
Yeah. Bye-bye.
Bye, everybody.
Thank you. Bye.